Imagine, if you will, a traveler. Not a tourist with a backpack, nor an explorer with a map, but a silent, frozen wanderer drifting through the unimaginable vastness of the cosmos. This traveler has been on a journey that predates the existence of our own human history, perhaps even the history of our planet. For hundreds of millions of years, it has sailed through the crushing silence of the void, passing between stars, weaving through the gravitational tapestries of distant galaxies, until finally, chance or destiny brought it to our doorstep. We call it Comet 3I ATLAS. It is an interstellar comet, a visitor from another star system entirely. And recently, for the first time, astronomers have managed to look deep into its icy heart and see something that has shaken the foundations of what we thought we knew about the universe. They found chemistry strange, unexpected, and thrilling chemistry that shouldn't be there. Specifically, they found an abundance of methanol, a simple alcohol, in quantities that defy the standard blueprints of our own solar system. This discovery is not just a footnote in a scientific journal, it is a whisper from a distant world, telling us that the recipe for planets, and perhaps even life itself, might be far more varied and rich across the galaxy than we ever dared to dream. The story of this discovery begins with the realization that 3I ATLAS was no ordinary rock. As soon as astronomers calculated its trajectory, the numbers screamed outsider, unlike the comets that are born and die within the gravitational embrace of our Sun, trapped in elliptical loops that bring them back time and time again. This object was moving with a speed and a path that could only mean one thing: a hyperbolic orbit. It wasn't falling into the Sun, it was just passing through. It was piercing our solar system like a bullet, destined to exit just as quickly as it arrived, never to return. This fleeting nature made it a prize of incalculable value. Here was a pristine sample of a frantic alien nebula delivered right to our backyard. To study it, scientists didn't use a standard optical telescope. Instead, they turned to one of the most sophisticated eyes humanity has ever built, the Atacama Large Millimeter Submillimeter Array, or ALMA. Located high in the Chilean desert, ALMA doesn't see light as our eyes do. It sees the faint, ghostly radio signatures of molecules vibrating in the cold dark. It can sniff out the chemical composition of a gas cloud from billions of miles away. When the researchers pointed ALMA at 3I ATLAS, they were expecting to see the usual suspects: water vapor, carbon monoxide, the standard exhaust of a warming comet. And they did find those things. But as they peered closer into the coma, that glowing halo of gas and dust that surrounds the solid nucleus, they saw a spectral signal that lit up their screens. It was the signature of methanol. Now, finding methanol in a comet isn't unheard of. We see it in our own local comets, those remnants of the cloud that formed our Earth and neighbors. But the quantity here was staggering. The concentration of methanol pouring off this interstellar visitor was far higher than anything typically seen in comets native to our solar system. It was as if the comet wasn't just releasing gas, it was saturated with this alcohol. But the mystery didn't stop at the quantity. The distribution of the gas was equally baffling. In a standard comet model, we usually expect gases to sublimate, to turn from solid ice to gas directly from the nucleus as the Sun heats it up. If that were the case, the concentration of gas should be highest right at the center and fade away smoothly as you move outward. 3I ATLAS refused to follow this script. While hydrogen cyanide, another molecule they detected, behaved normally and hugged the nucleus, the methanol was everywhere. It was spread out into the far reaches of the coma, forming a vast, diffuse cloud. This suggests that the methanol isn't just boiling off the surface. Something else is happening out there in the hollow. It implies that icy grains of material are being ejected from the comet and are fragmenting as they drift away, releasing their trapped chemicals slowly. Or perhaps the sunlight itself is driving complex chemical reactions within the cloud, synthesizing new molecules in real time. It's a dynamic, evolving chemical factory, operating in a way we rarely get to witness. To add another layer to the puzzle, optical telescopes noticed that the light reflecting off the comet was unusually red. In astronomy, a red hue often tells a story of age and exposure. It suggests the surface is rich in complex organic compounds or minerals that have been cooked by radiation. This visual cue matches perfectly with the chemical data. It paints a picture of an object that has been weathered by the harsh environment of interstellar space, a place where there is no atmosphere to protect you from the relentless sleet of high-energy cosmic rays. So, why does this matter? Why should we care about a booze-filled snowball from another star? The implications are profound because comets are the time capsules of a star system. They are the leftover bricks from the construction site of planets. When we look at a comet from our own system, we are looking at the raw material that built Earth 4.5 billion years ago. But when we look at 3I Alas, we are looking at the raw material of an alien world. The high methanol content suggests that this comet formed in a region of a protoplanetary disk, the swirling cloud of gas and dust around a young star that was chemically distinct from our own. Perhaps it was born in a much colder environment, where carbon monoxide ice was abundant. In the deep freeze of space, carbon monoxide can react on the surface of dust grains to form methanol efficiently. If 3I Alas came from such a nursery, it tells us that not all star systems start with the same ingredients. Some might be methanol-rich, seeded with a different balance of organic precursors. There is also the cosmic ray theory. As this object traveled for millions of years through the emptiness between stars, it was bombarded by cosmic radiation. This radiation can penetrate the outer layers of the ice, breaking chemical bonds and rearranging atoms. It's possible that the methanol we see today was actually manufactured during that long, lonely voyage. The cosmic rays could have transformed simpler ices into more complex organic molecules, building up a reservoir of chemistry that was waiting for the heat of a star to release it. If this is true, it means that the very act of traveling through interstellar space makes these objects more chemically complex. It means the galaxy is filled with carriers of organic matter, being seasoned and enriched by their journey through the void. This brings us to the most exciting connection, the origin of life. Methanol itself is not life. It's a simple molecule, toxic to us in direct consumption. However, in the grand molecular Lego set of the universe, it is a crucial building block. It is a stepping stone. From methanol, with a little energy and time, you can build sugars, amino acids, and the complex hydrocarbons that eventually form the scaffolding of biology. For decades, scientists have debated where the ingredients for life on Earth came from. Did they form here, in the primordial soup of our early oceans? Or were they delivered raining down from the sky on the backs of comets and asteroids? The discovery of 3I Alas adds weight to the delivery theory. It proves that complex organic precursors are not unique to our solar system. They are out there, drifting in the dark, locked in the ice of wandering comets. If a comet like this one could crash into a young, barren planet, it would deliver a massive payload of these prebiotic chemicals, potentially jump-starting the process of chemical evolution. In this light, 3I Alas is more than just a rock, it is a seed. It represents the potential for chemistry to evolve into biology. Its existence suggests that the universe is not just vast and empty, but filled with the potential for connection. The same chemical laws that govern a test tube in a laboratory on Earth are playing out on the frozen surfaces of objects light years away. The red appearance of the comet also hints at the presence of iron-bearing minerals. Some theories suggest that if you mix water, heat, and iron-rich minerals, you can catalyze the formation of organic molecules. If 3I Alas has an iron core or iron-rich dust, It implies that its parent star system had a heavy metal content, perhaps different from the mix that formed our Sun. This diversity is thrilling to planetary scientists. It means that when we look at the thousands of exoplanets we have discovered those worlds orbiting distant stars, we can't assume they are all built from the same standard kit. Some might be iron poor, some iron rich, some dry, some soaked in alcohols and organics. The variety of worlds is likely as infinite as the stars themselves. This discovery is a wake-up call for the scientific community. For too long, we have extrapolated everything we know about the universe from our single sample size, the solar system. We assumed our comets were the standard model, but nature loves variety. 3. IATLAS has shown us that our backyard is not the only design. It has forced us to admit that we have barely scratched the surface of what is out there. It also creates a sense of urgency. Interstellar objects like this are fast. They don't stick around. We have a very brief window, months, maybe a year or two, to observe them before they fade back into the darkness forever. We cannot simply wait for the next one because we don't know when it will come. It could be next year. It could be next century. This realization is pushing space agencies to consider a new kind of mission, the interceptor. Imagine a spacecraft parked in orbit, waiting dormant. Its sole purpose is to wait for the next interstellar alert. When a new object is detected, this hunter satellite would launch, using the gravity of planets to sling itself onto a trajectory to catch the visitor. It wouldn't just look from afar, it would get close. It would fly through the coma, tasting the gas directly. It might even drop a lander to touch the surface. Such a mission would be the holy grail of planetary science, to physically touch a piece of another star system without ever leaving our own. Until that day comes, we rely on our remote eyes like A.L. May. We rely on the patient analysis of light spectra and the creative deduction of chemists and physicists. The work being done on IATLAS is a testament to human curiosity. We are creatures standing on a small rock, looking up, trying to understand where we came from and if we are alone. So, the next time you look up at the night sky, remember that it is not a static painting. It is a busy highway. There are things out there moving through the dark, carrying secrets from places we will never visit. 3 IATLAS is just one of them, a messenger that briefly flashed its secrets at us before continuing its eternal voyage. It told us that the universe is rich, complex, and filled with the ingredients for wonder. It told us that, while we may live on Earth, our chemical heritage, the atoms and molecules that make us up, might have a history that spans the entire galaxy. The comet is leaving now. Every second, it puts thousands of miles between itself and the Sun. Soon, it will be too faint for even our best telescopes to see. It will become just another cold, dark wanderer in the void. But it has left its mark. It has changed our understanding. It has proven that even in the coldest, empty spaces, the fires of chemistry are burning, forging the potential for life in the dark. And that, perhaps, is the most beautiful discovery of all.